So recall that last time I was talking about cyclic groups. I showed that every subgroup of cyclic group is cyclic. Every subgroup of a cyclic group must be cyclic. Also, we have seen how many generators are there in a finite cyclic group. Uh, we have not talked about infinite case, which I will do it now. So mostly we have seen this, and also we have seen there exists a unique subgroup of order m for every divisor m of order of g if g is a finite cyclic group. Okay. So now let's come to this question for uh, the group infinite for any infinite cyclic group. So the answer is suppose G is cyclic and infinite. So which means that order of A is not finite, right? So uh, these are all distinct elements for all n, because suppose if there is some I and j for which both of these are same, then you will get this becomes 1 if this, and if I is less than this, you just get this becomes 1 depending on which of each of this. And this means that order of A is finite, right? Because in each case you get an upper bound of order. Either it is I minus j or it is j minus I, depending on whether I is greater than j or lesser than j. Anyway, so now uh, let's see how we can do it. So firstly, observe that if G is generated by A, then G is also generated by A inverse, right? Because take any element x from G, because it is generated by A, it will be some power of A, right? But same thing you can write it as like this. So we have it is also a power of A inverse. So G already has two generators. And now my claim is these are the only two generators. So either it is A or it is A inverse. It is fairly easy to see because let G is generated by some other element X. Now X must be some power of A because G is already generated by A, we know. And now so in case G is generated by A part T, and now A belongs to G, so A must be some power of A part T. Let's call that power K, which means this. So we get A is A part Tk. This is A power 1, and by this observation it has to be the case that Tk is 1. Otherwise, if Tk is bigger than 1, we get A part some finite power of A is 1, which means that order of A is finite, right? So Tk is equal to 1, and now we get that T is 1 and K is 1, or T is same as K as minus 1. So these are the only two cases because T and K are in integer. So we get that uh, so T and K both of them are either 1 or minus 1. So we get that G is generated by either A or A inverse, and we have already seen that these two indeed generates G, which means that these are the only two generators. So for an example, Z is generated by 1 and minus 1, and These are the only two generators. If you take any other generator, you will not get entire Z. You get something smaller than, strictly smaller than Z, some proper sub. So yeah, so these are the things that uh, I was planning to say on cyclic groups. Now let's let's build up some theory and more notations for uh, further topics. So let's start with some notations. So it's important to know these notations. So let me define centralizer of an element. So first, centralizer of an element. What do you mean by this? So let's take an element from G and we denote this by C of X. Centralizer means all those elements of G that commutes with X, right? And so the first thing to verify is that this is a subgroup, right? Oh, so now this is an easy thing to verify. I'm not doing it. And now the also another thing to observe is that if G is abelian, then X commutes with every element of every other element of G. It means centralizer of X is entire G. Second thing is what is center of G. This is these are uh, all those elements in G that commutes with any other element of uh, any other elements of G. So in particular, this is intersection of all those Cx. That is, it is intersection of all those Cx. Yeah. So if G is abelian, this means every element commutes with all other elements, meaning center is same as G, the entire group. So again, it is easy thing to verify that this is a subgroup. You can do it directly or you can use this fact because each Cx is subgroup and we know intersection of subgroups is again a subgroup. If you have not verified these things, you should do it because these are really fundamental things. And talking about intersection, also talk like you can think when union of two subgroups is a subgroup. This is also another uh, fact to observe. Maybe I will leave this. It's really easy. Now let's come to the main thing. So you've seen that center of G is G in case G is abelian. And if G is non-abelian, the center is a strictly smaller subgroup. And we will talk about these things in details in like in later videos. We'll see some facts about center of the group and we'll see when center is trivial and we'll also see some examples where center is trivial. Also when center is what is called a normal subgroup and all. So let's come to it. So first let me define what is a normalizer. Normalizer of a subgroup. So suppose you have a subgroup G of H and you denote it like this. So these are all those elements in G such that if you take this coset, this is left coset and you can also talk about the right coset. And when these two are same, we say X is in the normalizer of H. Again, easy thing to verify is that this is a subgroup. Yeah, and clearly H is inside the normalizer of H because every element, if you plug in any element of H, you get both of them as same as H itself, right? Because of the property of cosets we have seen. And if normalizer of H is G, then we say H is normal in G. So yeah, this is really important concept in group theory, what is called a normal subgroup. So in this case, every coset of every left and right coset of H in G are same in case it is normal subgroup. So again, an easy thing to check is any subgroup of an abelian group is normal, right? That is why is that? Because if you pick any subgroup H of G where G is abelian and any X, then um, you can write this, and this is just X H X inverse. But because it is abelian, you can interchange H, X, and X inverse like this, which is just you can cancel them and you get H again. Which means that XH is same as HX. So any subgroup of any abelian group is normal. Right. And also, let's see. So center of any group is normal in G. And for shorthand notation, we write say H is normal in G. We denote it by H, this triangle sign in G. Yeah. So we see as the center of G is normal in G. That is the logic is again similar because if you write this means what? This. Now H is in, so let me write it as G. Now H, because H is in center, it commutes with all the elements of the group G, which means H you can write it as X inverse H. Again cancel them, you get ZG. So again we get that any two right or left cosets are same. Yeah. Now, so we have these two facts about normal subgroup. Also, there is a sufficient condition. So, uh, says let H is a subgroup of G such that index of H in G is exactly 2. Then H is normal subgroup. So now, uh, let's see. So because H has index 2, G has two cosets, right? Because remember index by definition is the number of left cosets. So one of them has to be the identity times H, and let's say another one is like this. So we can write it like this. Yeah. And now we must show that, so to show it is normal, we need to show that any two left right cosets are same. So there are two of them. So H, this one is obvious because this is identity times H. This is same as this because this is H. And we just need to check that XH is same as HX. That is what we need to show. And now let's see. The first thing, first, observe that x square in H would imply that, so there are two choices, right? Because x square is in G. So x square is either in H or in XH, right? But this means x square is some x times H for H in H, and you cancel x, you get x is this, which is H. But this means XH is same as HH, which is H. But that is a problem because because these are distinct cosets, H and XH uh, are completely disjoint. So that is not true. So x square is not in XH. So the only other option is x square is in H. Right? And thus you can, now it's easy to see, right? Because then xh square would be just x square h. This means you are just squaring all the elements of xh, and this is h. And so xh, now it's like I don't need to do all this because x square is in h, so xh has to be equal to hx because hx has no other option. Like hx has to be one of them, and that because because x is not in h, it cannot be h, so it has to be xh. So like yeah, that's easy to see. And now so we get that this is true. And in fact, we'll see more general version of C later. Like this 2 is nothing special. You can make it more general, but that requires some more build up. So we'll see that after maybe some some videos, like 5 to 6 videos later. We'll see when we for that it requires the group actions and all. So we'll see that later. Uh, Now uh, let's compute some examples. So most of the groups that we have seen are abelian. So the center is the entire group. And so far the only non-abelian group that we have seen are the uh, GLNR and also MNR, right? And now you can uh, you can compute what is the center of GLNR or compute what is the center of a minor, but yeah, a minor again plus sign becomes so this is not really non-abelian. This becomes again abelian because addition of matrix is abelian commutative. So this is uh, but this is you can do it, and the answer is simple. It's just all those matrices, all the scalar matrices. Yeah, that you can do. One part is easy because if you pick any element, this element commutes with every other elements of GLN. That is easy. Just do the matrix multiplication. And for the other part, if you pick any element, say A, B, C, D, from the center, then uh, A, B, C, D commutes with all other matrices in GLN. So in particular, it commutes with this matrix also, right? And so this, if you just multiply, you get A, you get A plus B, you get C, you get C plus D. And this you get A plus C, B plus D, C and D. So just compare them and you get C is 0, A is D. So this matrix so far we get A is same as D, C is 0. And also this thing commutes with this element. It commutes with all the elements of GL elements, in particular this. And so the only thing we need to show is that B is 0. So let's see if this matrix helps or not. So this is just first thing, if you multiply you get B, you get A, you get D, and you get, let's see, C. And this is you get A, you get B. So we don't need to check the other things because C is 0, we get C is B. And because C is 0, we get B is 0. So indeed, this is a scalar matrix. So that is one easy thing to compute. So next time we'll talk more things in details about normal subgroups, and we'll move on to group homomorphisms and what are group isomorphisms and so on. So yeah.